Good evening and welcome to the last Science Week events for 2017. And tonight we have presentations from colleagues in Earth and Planetary Sciences. So there are two presentations before we have about half an hour's break for a drink outside, and then a further presentation after the break. So in the first half, Dr. Dr Strandmann, who is one of our joint appointments between UCL and Birkbeck, is going to talk about mechanisms for keeping the Earth habitable, which all sounds very important. And then one of his PhD students, Chen He, is then going to talk about triggering the radiation of early animals. And this is all in the overall theme of what controls the Earth's long-term climate. So probably as Earth Sciences, this is probably not going to tell us what the weather's going to be like at the weekend, but probably in thousands, if not millions of years. So, Philip.
Thanks very much. Yeah, so this is what Nick just said in terms of outline. So we're going to try and tell you why life is around on the Earth and why the Earth has carried on generally keeping life, but has had blips and changes in time as well. And so I guess overall we as scientists, but also as a species, have a scientific problem, which is this blue-green planet here. And it really is hard to explain why it exists, why it's still blue-green, so why life is still here. And so in general, that there's a quote from Mark Twain that I found: the two most important days in your life, the day you were born and the day you find out why. And so, I'm not going to tell you why you were personally born, of course, but understanding why life is still here, why it hasn't gone extinct, obviously means culminating in why we as a species are on the planet as well. So, if we think about the terrestrial planets in our solar system, the ones we can more or less directly compare to, we obviously have three. We have Earth in the middle, we have Mars here on the right, cold, and Venus here on the left, which is hot. And clearly, Earth is the only one that has any sort of oceans, life, green, blue colouring to it. But almost more interestingly is that very early on in the history of the solar system, when these planets formed, they were all pretty much similar. We all believe they started out with liquid oceans at their surface. And then clearly, now, the Earth has kept that ocean, and Venus and Mars have lost it. And so, the question is, why has the Earth managed to keep its oceans, its liquid water, and therefore its life? Because all the life that we can sort of envisage and understand really depends on some degree of interaction with water. And so the other point is, of course, that the age of all the terrestrial planets, Earth, Venus, and Mars, are pretty much the same. And just to emphasize, yes, obviously we know what Earth looks like. Mars is a desert that once had water. There's evidence of rivers and oceans and glaciers that we still find on Mars with the satellites and probes we send there, but there's no liquid water anymore. And Venus, which effectively is in a runaway greenhouse state, so its ocean is now basically in its atmosphere. It has incredibly high atmospheric pressure and incredibly high temperatures, which is why all the probes you send there last a few minutes before they get crushed and boiled, effectively. This is one of the last ones, the Soviet Venera 9 lander, which managed to survive about 8 minutes on the surface before it was destroyed. And most didn't even make it to the surface. So the question, therefore, is, what do you need, first of all, for a life to exist on a planet? And one of the points is you need a planet of the right size, clearly, because you can't have a massive gas giant such as Jupiter or Saturn, because their gravity is so high that life as we could envisage it couldn't exist there. And that means you need a planet in the right place in the solar system, because the terrestrial planets exist close in the rocky, sort of metallic planets exist close into the sun, for a specific reason, which is that in your pre-solar nebula, something like this, with Archer's impression of where your sun starts off, this is sort of very early and before the solar system properly forms, and you've got a rotating disk of gas around that, which gradually accumulates to make your planets. And there's obviously a strong temperature gradient. It's hot close into the sun and cold way out from the sun. And so the temperatures at which metal and rock can precipitate out of the nebula are the temperatures close in, which is why all the terrestrial rocky planets are close into the sun. And the gas giants and out of water and hydrogen and helium exist further out because that's where those gases and water can precipitate out of the solar system. So Jupiter, for example, exists pretty much at the point at which water can condense out of the solar nebula. And it's scooped up all the water and therefore it grew that large. So you need to be in the right place in the solar nebula. I've just put this picture here on the right because to my mind it's actually one of the greatest photographs ever taken. It's actually a photograph of what a solar nebula is. So this is an artist's impression, this is an actual photo taken in 2014 down one of the large telescopes in South America. And so the first time it actually proved what we had theorized for quite a long time, that a pre-solar nebula does exist of a protosun in the middle and a sort of flat rotating disk of gas. You can see the tracks of the planets are beginning to scoop up dust as these small planets begin to form. So a great photo that sort of proves the point that it doesn't matter where the planet is in your solar nebula. The other is, of course, to have life, we need, as I said, some degree of liquid water at the Earth's surface. Scientifically, we can only understand life that has an interaction with liquid water. It goes into the realm of science fiction if you want to imagine life outside of that, but we have no concept, no scientific way of theorizing that sort of life. And so, again, it's a temperature matter, because Earth, with an average temperature of about 15, is just right. Mars is down at minus 55, and basically Mars was so small that it lost its ocean and atmosphere through impact with solar rays. So the atmosphere and ocean were ablated off by solar rays. Venus is hot and very high pressure because it's in a runaway greenhouse state, and its ocean has basically evaporated and ended up in its atmosphere. And Mercury doesn't really count in this. So we need some way of keeping the temperature of the planet within the bounds necessary for liquid water, at least for even life to have a chance of survival. And so something makes the Earth obviously unique in that matter. We can take that a step further. This is a plot just showing the atmospheric composition of the different terrestrial planets. Here's Earth now, mostly nitrogen and about 20% oxygen. But the original Earth had an atmosphere that was almost entirely carbon dioxide. And Mars and Venus had the same sort of atmosphere, dominated by CO2, which is what you'd expect because the original atmospheres are from volcanic eruptions, which are generally gases like carbon dioxide and carbon monoxide. So effectively, again, Venus and Mars have kept their original atmospheres in composition roughly, and the Earth has dramatically changed. And the question, therefore, again, is why, and why has that also maintained itself over time? And so we know that the Earth is around about 4.5 billion years old. So the question then is, we have this 4.5 billion year Earth. How long has life existed? If you want to understand how the Earth has been kept habitable, why the Earth is still habitable, we want to know for how long that might have occurred. And so if we think about sort of ancient life, the sort of first image you might come up with is some, dinosaurs, if you think about old life. I always show this image as painting simply because it's completely inaccurate. Because T-Rex existed closer in time to us now than it did to Stegosaurus over here. There's obviously 100 million years difference between the two. So it looks great as an artist's picture, but they never actually met by 100 million years. But so 150 million years ago we had dinosaurs roaming the Earth. We can go back even further, 600 million years ago, to what's known as the Carafauna, and Tian Shan will talk about that a bit later on. We find these a lot in fossil evidence. They've been described as sort of pizzas crawling around on the ocean floor. We don't really understand how they operate or exactly what they were. We think they were animals of some sort, soft-bodied animals, but we have no real concept of how they ate or reproduced or anything like that. So about 600 million years ago, we're entering the realm of species on the Earth we don't really understand anymore. And so if we look at a timeline of Earth, this is the sort of thing you might have seen before, where Earth starts at 12 o'clock and then time goes all the way around and finishes at 12 o'clock, if you like. then we know that we start existing at sort of 10 seconds before midnight or something like that in this sort of graph. You see dinosaurs start existing between about 1130, and those sort of those Ediacaran fauna I talked about just now are about maybe about 10. Multicellular life from maybe 8 o'clock, but life itself exists from back here. So from maybe 1:30, 2 o'clock in this graph. So that means that sort of 85 to 90% of Earth's existence has been inhabited by life. And I always think, every time I say that, I always think that's a remarkable statistic, that for over 4 billion years, the Earth has had life on it. For its entire life, there has been life on Earth. And in fact, there was a study that came out a couple of weeks ago that claims to have found evidence of life back at sort of 4.3 billion years back here. So those barriers are being pushed back further and further. It means that for almost all its life, the Earth has been inhabited. And that means that we have to explain how life has survived for so long on the Earth, because there have been all sorts of different changes on the Earth at the moment, huge environmental changes, meteorites, etc. And the question is why that hasn't wiped out Earth. So maybe the first question is, when do you start getting water on Earth? Because obviously life requires water, and we want to know at what point we think that the Earth might have started being inhabitable. And one of the ways we can do this is to look at a mineral called zircon. Here it is in gem form. This is a sort of slightly more scientific image of an electron microscope scan through it. And the point about minerals such as zircon, they're produced by volcanoes. And if you have a volcanic rock that's erupted onto the Earth's surface, eventually sort of water and wind will erode it down, and those crystals, those mineral grains that are in that rock, will be transported through rivers and eventually end up maybe in the oceans and make something like a sandstone. And then eventually that sandstone will be uplifted again and eroded down again and broken up, and maybe some of those grains will end up in another sandstone. And then every time that happens, those minerals obviously get smaller and more abraded and cracked until they disappear completely. And so things like quartz can go through several episodes of being in a rock and then uplifted, eroded, being another rock. And that's mainly why quartz is quite tough, which is why sandy beaches are made out of quartz. But zircon is really tough. So as tough as, not tougher than diamond, which means you can go through a lot of these cycles. Which means in quite young rocks, we can find zircons that formed right at the beginning of Earth history. And that gives us a window. The chemistry of those minerals gives us a window into the very early Earth. And so this is a plot of, time. So here we have 2.8 billion years, here we have the formation of the Earth at 4.5 billion years. And what people have done is taken some of these very old zircons that have ages very close to the formation of the Earth, and measured the oxygen isotope composition. And that's not something I'll go into in any detail, but broadly, you can measure isotope ratios in minerals, and natural processes change these isotope ratios very subtly relative to each other, and they provide us a window. And so the oxygen isotope composition, the mantle, the igneous rocks, the volcanic rocks, is basically this red dotted line here. So if there was no change in the chemistry of these zircons, they'd have composition of this dotted line here. But you see they're clearly pretty much all higher than that line. And basically the only way you can increase the oxygen isotope composition of these rocks is by interaction with liquid water at low temperature at the Earth's surface. So what this is telling us is that even by about 4.3 billion years, we had an ocean on the Earth. This is very rapid. This is 200 million years after the Earth actually formed. We have during all this time, we have things like the moon and the giant impact that caused the moon. This is a really rapid cooling of the Earth and a liquid ocean at that point too. So those sort of arctic impressions you have of massive magma oceans and comets falling in, everything glowing and volcanoes going off, is actually only for a very, very short period in Earth's history. And after that, the whole thing stabilized and we had water on the Earth. So that puts oceans about here on this graph, so very early on. And we have obviously clearly enough time, even for the newest estimates of when life formed, which is about here, so we clearly have liquid water sometime before that. So that sort of works. And then, as I said, we have 4 billion years of rather dynamic history in the Earth. We have obviously huge meteorite impacts. The famous one is the one that destroyed the dinosaurs, but there's been bigger ones in Earth history. This is a crater from a relatively recent small one. We've had time periods when the Earth has been completely covered in ice. The ocean's been frozen, we had ice at the equator, periods known as snowball Earth. We've had the opposite when we've had global deserts and no ice on the Earth. We've had huge volcanic eruptions, one's big enough to cover the continental North America with lava 2 kilometers deep. And despite all of this, life has managed to survive. And it's not just these catastrophic episodes. Overall, the chemistry of the Earth has changed dramatically over time. This is a plot. Over here is the beginning of the Earth 4.5 billion years ago. Over here is the present. And so these lines are various chemical changes. So this red line is the oxygen content of the atmosphere. So you start off basically at 0. And gradually, in 2 main episodes here and here, the oxygen content increased towards the present day. That's a big change for life, because you may know that for very early life, oxygen is a bit of a problem because it's quite a reactive gas. As you know, if you stick any sort of iron sheet out, it'll rust and burn in oxygen. So it's a big change from an atmosphere over here to an atmosphere here or here. Same time, carbon dioxide in green decreased over time. That means temperatures will have changed. And you can see temperatures in this blue line here. These sort of decreases are these times when we had these snowball Earth events, when the Earth was entirely covered in ice, which happened a couple of times in Earth history. And also this black line shows the luminosity of the Sun. The Sun has increased in brightness and the heat it gives by about 25% during the course of its and Earth's life. So the heat coming in from the Sun has increased over time too. So not only has life had to deal with sort of things like volcanic eruptions and meteorite impacts, these sort of catastrophic snapshot events, but you've had these huge gradual changes too, in the income amount of heat coming in, the change of oxygen, the change of CO2, and other gases as well. If you want to look at the temperature a bit more in detail, this is an estimate for the last 3.5 billion years, the average temperature of the Earth's oceans. And you can see there's a lot of variation, a lot of wiggling going on, a lot of quite rapid changes. But if you look at the scale between, on average, between about 10 and 35 degrees. So for 3.5 billion years, that's 25 degrees variation. That's actually remarkably stable. Given what we know happened to Venus and Mars on this scale, Venus is several stories above us, and on Mars is several stories below. And so despite those variations, it has to be said that a lot of these more recent variations have caused mass extinctions. They've caused changes to the amount of animal life and the type of species on the world. But generally, this is very stable. And the question is, A, what has allowed this stability to occur? And B, why haven't any of these changes, this sort of dramatic increase here or this dramatic decrease here, why haven't they carried on? Why haven't they ended up at a point where life can't exist anymore? Why has the Earth been kept stable as well? So in other words, what makes the Earth unique? One aspect of that, compared to the other terrestrial planets we know about, is plate tectonics. So you've probably heard about plate tectonics, this idea that you have a lot of plates that carry the surface on the Earth, and they move around relative to each other. And when they pull apart, you get crust forming, mostly in the middle of oceans. And when they collide, you either get one slab dipping down beneath the other and going back into the Earth, or you get them colliding and building mountain belts. And the point is that plate tectonics doesn't just give us changes in mountain belts and the amount of crust, it also keeps the gas cycle going, because when you subduct one plate, it takes water from the oceans with it, takes water and gas, CO2, back into the mantle, and eventually that gas will be re-erupted from volcanoes. So plate tectonics keeps the gas cycle from stagnating, the water cycle from stagnating. Now it is telling that neither Mars nor Venus have plate tectonics in the same way as Earth does. Mars probably doesn't have any plate tectonics. Venus maybe has some, but it's too hot really to have the same sort of plate tectonics, because the Earth's plate tectonics does rely on having a cold ocean above it, because water lubricates the movement of the slabs as well. So we need plate tectonics. So plate tectonics is clearly very important for allowing the Earth to be habitable. But in terms of allowing the climate to recover from these sort of rapid events, plate tectonics is too slow. So it's hundreds of millions of years of plate tectonics to sort of react to anything, and therefore, while it's a process that has allowed the Earth to be habitable, it cannot be the process that has kept the Earth habitable through various catastrophic events. The other problem is that plate tectonics, as far as we understand at the moment, starts probably around 3 billion years ago. So there's a good chunk of Earth history where there was life, but probably no plate tectonics that we have to explain in any case. There's another potential theory about why the Earth might be habitable. One you may have heard about called the Gaia theory. And this was proposed in the 70s by Jim Lovelock and Lynn Margulis, and wrote a number of books on this as well. And the idea was that life regulates the environment of the planet to make it more habitable. So the quote is that life is a self-regulating system that manipulates the physical and chemical environment to maintain the planet as a suitable home for itself. And it's clearly undeniable that life has changed the planet. You just have to look at rainforests or plankton in the ocean. You know, the change in the amount of oxygen cycling through photosynthesis, obviously a huge change to the planet. Whether life is actually actively changing the planet to make itself more habitable is another big question. For example, people like Richard Dawkins, probably one of the most famous people who do not think the Gaia theory works. And his argument is that the Darwinian idea of evolution, this idea of a selfish gene, is that the planet is not a unit of selection, so that each species is effectively striving for itself, its own species to survive. There's no reason why one species should manipulate the planet so that another species survives better. And so there's a lot of debate going on about this. I will briefly give the original thought experiment by Jim Lovelock about how this might work. And that's a thought experiment called Daisy World. And the idea is if you have a planet that's only inhabited by daisies, some of those daisies are white and some of those daisies are black. And they're broadly in equal proportion. And then let's say, for whatever reason, white daisies begin to expand and gain dominance. But the point is that white daisies are white, so they reflect more sunlight, which means the planet will begin to cool because more sunlight is reflected back. And at the same time, the white daisies will cool down faster because they're reflecting sunlight where the black daisies are absorbing it. And so that means the white daisies will begin to die out and the black daisies will begin to take over. And same the other way around, as the black daisies take dominance, the planet begins to heat up. The black daisies suffer more because they're heating up more than the white daisies, they die off, and the whole thing returns to equilibrium. So the idea is you're sort of oscillating around a sort of a steady state this time. And that might work. There are a lot of people who still believe that the Gaia theory works. A lot of very hardcore supercomputer modelling has been going on into understanding whether this could work on a sort of more complex field as well. But even so, when I say it's undeniable that life has strongly affected how the Earth works. There are probably a good amount of time, at least a billion years or so, where life just wasn't enough of a force to manipulate the planet to the degree to allow itself to survive. So even if this does work, and I'm personally not convinced by the Gaia theory, then there are big chunks of Earth history where it couldn't have worked in any case. And there are alternative theories. There's one called the media hypothesis, which has the opposite idea, that single cellular life is trying to kill multicellular life, in effect, throughout Earth. Now there are a lot of examples out of this, the ones, the oxygenation of the planet is the main example, where oxygen production by single cellular life caused a big problem for multicellular life and caused a big mass extinction. And the guy who proposed this, Peter Ward, argues that quite a lot of the mass extinctions are effects between interaction between single cellular and multicellular life. There's a lot of dispute and ambiguity around this sort of idea. But what I'm going to try and explain to you is that I don't think we need all this. There are actually relatively simple ways we can keep the Earth habitable without any sort of this fooling around with trying to understand what plants do and data at various times. And that comes down to the temperature of the Earth. In particular, and I'm sure you know, we care a lot about the carbon cycle as affecting the temperature of the Earth. And I'm not necessarily talking about this sort of carbon cycle that we talk about when we talk about global warming, where factory emissions emit CO2 and then we plant trees and that makes everything fine. It doesn't, I should say. But what I'm talking about is the long-term carbon cycle, the one that operates on 10,000 years or more. And that's a relatively simple system. Carbon dioxide is put into the atmosphere by volcanoes. Every now and again a volcano goes off, or whatever size, and puts CO2 into the atmosphere. And that will create some degree of global warming. And carbon dioxide is removed from the atmosphere and the oceans, because the oceans and the atmosphere basically make one unit, by two processes. One is the formation and burial of organic carbon. Coal, oil, gas, black shale, organic carbon in rocks. And that takes organic carbon and buries it out of this ocean atmosphere cycle. And that's of course why burning fossil fuel is such a problem, because we're taking organic carbon that's been removed from the system and putting it back into the system, hundreds of millions of years later. The other is the formation of rocks such as limestone, calcium carbonate, what most of London is built out of, or the grander bits of London is built out of. And that C in the carbon is carbon, and so that formation, coral reefs, whatever else, takes carbon out and also locks it up. And again, that's why things like ocean acidification, which dissolves this carbonate, is a problem, because that also adding CO2 back into the atmosphere. And so if the input of CO2 is effectively random, every now and again a volcano goes off, then it sounds like we have to think more about the removal process of CO2 if we want to understand mitigating the climate. And so the question is, what controls these two processes? And it turns out that the key process controlling these is the weathering of rocks on land. You have rocks on land being dissolved by rivers, by rain, because that process washes nutrients into the ocean, which allows you to make organic carbon through plankton and life, which buries it, and provides the chemicals and the carbon, I'll show you in a moment, to make carbonate. So it's a dissolution of rocks on land that actually turns out to be the key process controlling climate on long term. And this basically works like this. This is I won't go into too much detail of the chemical formula, but it's actually a rather simple and elegant system about how this works. And effectively, if you have a limestone on land, anything what London's built out of is calcium carbonate, CaCO3, and you dissolve it in water. To dissolve carbon in water, you require bicarbonate to form, HCO3 minus. Right? And you'll see if this is a bottle or a bottle of water, you'll find on any bottle of water you'll find a list of elements like calcium or magnesium concentration. Among those will always be bicarbonate. And that bicarbonate is dissolved atmospheric carbon dioxide in the water. So to make bicarbonate, which has basically two C's in it, you require another carbon dioxide which comes from the atmosphere. And then that's all washed from the continents into the oceans by rivers, and you make limestone again, which means that the carbon you've taken from the atmosphere eventually goes back to the atmosphere. So carbonate weathering, limestone weathering, on the time this reaction goes to completion, which is about 10,000 years or so, has no net effect on CO2. It does on timescales shorter than 10,000 years, so it is a constant important effect, but on longer timescales has no net effect. However, if you dissolve a silicate rock on land, something like a basalt or a granite, that contains no carbon. So for the same reaction, to get these two carbons, you need two carbons coming out of the atmosphere, of which eventually, when they enter the ocean, only one goes back to the atmosphere, and the other stays in limestone. So the weathering of silicate rocks on land is a net removal process of atmospheric carbon dioxide. And that means that hopefully that silicate weathering is the key process that controls long-term climate. Okay. So basically what we're saying is this: you take some sort of calcium magnesium silicate rock, a basalt or a granite, you react it with water, which dissolves CO2, and you make some sort of limestone. The cliffs of Dover, for example. An example of limestone rock that consists out of locked up atmospheric carbon that was locked up about 100 million years ago. And weathering itself, therefore, is a key and critical important process in controlling the climate. And you can see weathering all the time. If you're seeing a limestone pavement or the formation of caves, this is all the dissolution of rock by water. This is weathering. Or the formation of a mountain belt. So without weathering, a mountain belt would just be a high plateau. It's weathering that creates all this this mountainous part of it. So it's an important process in forming the Earth's surface as well as controlling the Earth's climate. And then the question therefore is, okay, weathering, we say weathering is the key process removing CO2 from the atmosphere. And we also know that when a volcano goes off, we add CO2 to the atmosphere, that warms the atmosphere. So then the question is, can the two processes just carry on normally all the time? If you have Occasional volcano goes off and adds CO2, and all the time in the background weathering is going on and removing CO2. Would that be enough to keep the Earth habitable? And the answer is no. So this is a model for atmospheric carbon dioxide concentration against time, both on a log scale. This is in millions of years, so 1 million years, 100,000 years, 10,000 years, and atmospheric CO2. And it's a model for two starting compositions. This is pre-industrial CO2, this is 10 times that, is a random number. And what the model does is calculate what would happen if there was an imbalance between CO2 input and CO2 output from the atmosphere. So if there was a 25% excess in CO2 input into the atmosphere, this is what would happen to these two models. You can see that CO2 would very rapidly increase. So within a few tens, 100,000 years, you get a large change. Within maybe a couple of million years, you get an irreversible greenhouse effect. Venus is up here. This is what would happen if there was 25% excess in removal of CO2 versus input. You can see within 10,000 years, you're dramatically cooling the climate. Within less than a million years, and an irreversible ice house event. Mars, in effect. So Venus is up here, Mars is down here. Earth has kept itself very, very tightly in those margins. And that means that input and output can't be two random processes. They must be controlling one another. And effectively, if we say that the input is CO2, volcanic eruptions, they go off randomly every now and again. The input is random, the output has to be a control mechanism. And this is actually the mechanism that we think broadly kept the Earth habitable. It's actually rather a neat and elegant solution. If we say we have a warm climate due to lots of CO2 in the atmosphere, so high CO2 creates a warming event, that's sort of what we're worried about now. The warmer things are, the faster chemical reactions go. That's a simple physical law of the universe. Chemical weathering of rocks is a chemical reaction. So the hotter it is, the faster chemical weathering will go. Chemical weathering removes CO2. So the faster chemical weathering goes, the more CO2 it removes, and therefore it cools the planet. So the more CO2 you have, the warmer, therefore the more CO2 you remove, and it cools down again. That works the other way around too. If you have no CO2, the climate is cold, chemical weathering will be less, CO2 will be removed less, and CO2 will gradually build up again from volcanic eruptions. So that gives us a really neat mechanism for stabilizing the climate, and gives us presumably the mechanism why the Earth is still habitable, because every time we get some big event going on, weathering will increase or decrease and stabilize the planet and the climate quite nicely. And that broadly will explain why the Earth has been kept in narrow conditions necessary for life over so long. So broadly what we're saying is happens this. For example, you get a big volcanic eruption, rivers will then increase their weathering because it's warmer, and you form carbonate in the oceans, something like the White Cliffs of Dover. I'll briefly give you an example of this, because obviously one of the questions now is, well, how quickly does this operate? How quickly can weathering stabilize the climate over time? Can we do it in 5 years, or does it take 5 million years? And that obviously, as I'll talk to you a bit further on as well, obviously matters for the future as well, what we think will happen to a warming planet. So this is an example this is Beachy Head on the south coast of the UK. And you may not know this, but Beachy Head represents a large global warming event called a hypothermal. It lasted a few 100,000 years and was caused by a big volcanic eruption. And also a big mass extinction. About 30% of all marine life went extinct, basically about halfway up this cliff, when it was in the oceans, obviously. So it's a time period to try and examine what happens when you warm the planet due to carbon dioxide and see what the results are. I'm not going into too much detail about how we work out what weathering does, but we use the isotopes and element of lithium, because lithium is only in silicate rocks, not carbonate rocks, so that's the bit we care about. But broadly, this is time in 1 million years up here, and as this line decreases, we're increasing weathering. From the onset of CO2 release by the volcanic eruption, so weathering is increasing until it reaches maximum weathering after almost 300,000 years. And then it starts decreasing again. So this is the point at which weathering has taken over control of the climate and has mitigated so far the climate is then cooling again, in effect. And that takes a few 100,000 years, which is rapid on geological timescales, but rather slow on any timescale we might hope to use this in the future. Okay, so we have this wonderful mechanism for keeping the climate stable and the Earth habitable. But there's a corollary to that argument, which is if we have a mechanism to keep the climate stable, why has climate changed over time? And we know it has changed over time. This is quite a nice graph because it shows the Earth's time over the last 500 million years in sort of distinct slices. So this is the last 2,000 years of the warming creating now, and the Little Ice Age, which is when broadly the Thames froze over, sort of Victorian, early Victorian period of cold. Going back to another slice for about 10,000 years, we have a climatic optimum in the medieval period, and which has sort of allowed sort of expansion around that time. Back another 500,000 years, you can see the oscillations, which are the Ice Age events, effectively. And then back to 5 million years, you can see you still have these oscillations, but gradually the planet is warming. And then another slice back to 65 million years ago, this is when the dinosaurs died out, and you can see we have a general warming back in time over that period. To here, where we basically this is a hot house period where there's no ice broadly on the planet. In the last 500 million years ago, we have a lot of changes. And so, if we think we have this temperature control and weathering and therefore the climate, we shouldn't really get it. We should get a nice flat climate with occasional brief spikes as volcano goes off, and then weathering brings anything back under control. We shouldn't have hundreds of millions of years of change. But there has to be another process going on. And that actually brings us back to this plate tectonics that I talked about earlier, and the fact that Earth has it and neither Mars or Venus has it. And the idea that, especially in plate tectonics, at some point or other, continents will collide and form mountain belts. And so it turns out that mountains are another big control on the climate. Again, actually through this weathering control. So you probably know that around about 50 million years ago or so, India collided with Eurasia to start making the Himalayas. And that collision between those two tectonic plates started uplifting and forming the Himalayas. And what we see, this is a plot of temperature from 65 million years ago. This is when the dinosaurs go extinct to the present day. You can see that from about 50 million years ago all the way to the present is generally a cooling trend. Not at all coincidentally, the Himalayan uplift starts about 50 million years ago. So Himalayan uplift starts and the planet begins to cool, and then eventually we form the Antarctic ice sheet, which is what Andy is going to talk about after the break, and then we form the Northern Hemisphere ice sheet about 5 to 10 million years ago, and cool the planet even more dramatically. But this transition from a greenhouse planet with basically no ice, and a global rainforest if you like, to an icehouse planet with glaciers and glaciated poles as we enjoy today, occurred over about 50 million years, and it coincides with the uplift of the Himalayas. So what actually turned out to have happened is that uplift of mountain belt increases the Earth's surface area. So it simply increases the surface area for chemical weathering. Chemical weathering removes CO2, so if you increase it, you drive the cooling away. So basically what's happened is the same mechanism that stabilizes the Earth, which is chemical weathering, has been manipulated by another event, which is the increase of the Earth's surface area. So basically, every time you lift a mountain, you increase the Earth's surface area, lift a mountain belt, or you grind things with glaciers, you increase weathering, that will remove CO2 and drive the cooling event. So very basically, this temperature feedback event keeps the Earth habitable. But if you want to drive the Earth from one background climate state to another, greenhouse to icehouse to greenhouse, whatever, that requires another sort of tectonic event that overrides for a while that weathering feedback. Okay, so broadly speaking, therefore, the temperature feedback is a process that has kept the Earth habitable. And this mountain building override is one that has actually driven the Earth into different states, and therefore has actually caused mass extinctions and forced the evolution of life over time, because life has to adapt to these climatic changes with time. Okay, just for the last 5 minutes, I'm briefly going to talk about what this means for the future of the planet. You all know that CO2 is increasing. This is a trend from Mauna Loa Observatory of carbon dioxide concentrations. You probably know that in 2013, famously, we first time hit the 400 ppm boundary. Bearing in mind we started off pre-industrial at 280 ppm CO2. Last year was the first year CO2 did not go below 400 ppm. And this is the reading from Mauna Loa as of 4 days ago, 408 ppm. So things are increasing rapidly. This is also just to make the point of temperature. This is an animation of the monthly average temperature of the last 150 years. Watch that. Let's go through that again. So you can see each decade is effectively in a different colour. And it's very clear that the last few decades have been rapidly warming. And each, basically in the last few years, almost every year has been a record-breaking hot year every time. But broadly fair to say that we have a bit of a problem, I should say. But this is, the last one is March 2016, so almost a year ago we probably breached this 1.5 degree barrier since then. Other matters, so people talk about that, okay, climate change creates different climate belts, but that's sort of fine because then Siberia can bring in growing grain, and that will be, we'll still have, if grain is dying out in parts of the steppes, then we can grow it in the northern parts. And that doesn't work because, of course, you can only grow things like crops on soils that are already formed, and it takes millions of years to form a soil. This, for example, is a prediction of rice growth in Southeast Asia, with the red and the yellow is loss of area due to climate change, while the blue and the light blue and the dark blue and the green are areas gained through to climate change, because obviously warming will allow things to move northwards from higher altitude. And there are changes, but overall the change production will decrease by about a quarter by 2050. So, it's not just, the problem with climate change is not just a matter of, in the developed world, of increasing your thermostat, slightly, or your air conditioning in your house, because the crops we survive on, the rice, the wheat, maize, bees, which pollinate all our crops, are all strongly climate dependent. The water production as well, the monsoon. So it's not just a matter of building a house higher with better cooling and better insulation. All the things that we survive on are also strongly being affected by climate change. In terms of prediction, this is, prediction up to 2300, but the different scenarios, this is where we are now, and this is from the International Governmental Panel on Climate Change. This pathway here is known as the business as usual pathway. If we do nothing, this is what happens, which is 8 degrees by 2300, which is probably, in terms of what we survive off, it's not broad enough survival event for humans. But you can see that we have scenarios down here, which are the ones that we're trying to aim for under the Paris Agreement, with 1.5 to 2 degrees warming. The one problem is that these scenarios cannot occur unless we also actively remove CO2 from the atmosphere. It's no longer enough that we reduce emissions, we also have to actively remove to meet these scenarios. And there we come into the process of what's known as geoengineering, the process of actively removing CO2 from the atmosphere. And there are lots of different scenarios for doing this. None of these are particularly far advanced. The most far advanced sort of in small pilot stage studies or lab experiments. And there are crazy ideas like space mirrors or increasing clouds. But there are others which might make some degree of sense. And ones like manipulating the carbon cycle as it already is and making it go faster. One is ocean fertilization, so increasing that formation of organic and burial of organic carbon, so increasing that natural removal pathway of CO2. The other is increasing weathering. If you grind up rocks and very fine and spread them on fields, that might increase weathering enough to remove some CO2. Or there's another one which we're also working on called CarbFix, which is mineral carbonation. So you artificially make limestone in rocks to reduce CO2. This is a process that we've been working on in the industrial pilot scheme in Iceland, and effectively we're pumping liquid CO2 into rocks and then precipitating limestone in those rocks. So here's a drill core that we did, and the black is sort of basalt from Iceland, and the white is limestone that we precipitated. So there are methods for removing CO2. The problem we have, and a lot of these, perhaps the best ones that might work, are methods just enhancing various aspects of this natural carbon cycle, speeding various aspects up to remove CO2. The drawback is, of course, that climate change is effectively an uncontrolled experiment we don't understand. So adding another potentially uncontrolled experiment we don't understand through geoengineering is a big risk. So at the moment, the sort of idea is we should research geoengineering but not implement it until we actually reach a point we realise there's a point of no return. If we don't do something immediately, then we have a problem that species could well not survive. Tipping points in the climate. So just to summarise all that, well, the Earth developed life probably because it was large enough to keep water, some degree of plate tectonics, and, well, some degree of luck in organic molecules. We know that amino acids have been found in solar nebulas and meteorites, so some aspect that brought in these organic molecules to form life. But the Earth kept life because of this weathering thermostat. And not only is it allowed the Earth to stay habitable to allow us to survive, but it may also be an aspect that we can exploit to keep the Earth broadly habitable in the future too. That's it. Thank you very much.
Time for a few questions. No? Yeah.
Do all the experts agree with your analysis?
Of which part of that? So it's the idea that weathering controls...
Well, the carbon cycle and weathering, yes.
Everyone agrees that it is probably the main process that removes CO2. What we don't agree on or don't really know is exactly what controls it. So the idea behind temperature controlling it and uplift controlling it sort of works, but if you want to say, what amount of increase in temperature will give an amount of increase in weathering or vice versa, then it gets more tricky. And the exact timing at which it operates also may depend on the climate it's under and other conditions as well. So the detail is still very much unknown. The general process is generally agreed upon.
Okay, if there are no more questions, we'll move on to our second speaker.
Excuse me, can I just ask?
Yeah, sure.
When is the time that you think we'll have to do something, your geophysics?
If I knew that, I could claim my Nobel Prize now, I think. Don't know, but there are a number of tipping points, such as methane release from sea floor and from bogs and the tundra, and ocean circulation change, which we know have happened in the past and we know have caused the climate change consequences in the past, and that we're seeing beginning to happen now. And so there is a possibility, and we don't really know, that in the next 10 to 20 years we could hit a sudden point at one of those. Yeah.
So our next speaker is Chen He, who's going to talk on triggering the radiation of early animals.